Alright, so here we have a data set X of shape D comma N, which means there are D rows and N columns, and each column is a data point. Now it says that the kth principal component of the data set can be written as Wk equals summation of alpha I xi, where xi is the ith data point and alpha i's are all scalars. Now I can write it differently as x times alpha, right? Where alpha is a vector comprising of alpha 1, alpha 2 up to alpha n. The same thing, I'm just changing the notations. Now they're saying that the kth largest eigenvalue and corresponding eigenvector of x transpose x are given. Let me call them as lambda k and vk. Okay. But remember, these are the eigenvalues and eigenvectors of x transpose x. And we have to find the eigenvalues and eigenvectors of xx transpose, because this is our covariance matrix. In fact, the covariance matrix is 1 by n times this, right? But how are the eigenvectors and eigenvalues of x transpose x and xx transpose related? That we will see now. So if lambda k and vk are an eigenpair of x transpose x, then what we can say is that x transpose x times vk will be same as lambda k times vk. Now if I multiply on the left with x, I'll get x transpose and then x vk same as lambda k times x vk. Now what does this mean? This means that x vk is an eigenvector of this matrix xx transpose corresponding to the eigenvalue lambda k. So this means that lambda k comma x vk is an eigenpair of xx transpose. Now one thing to be observed is that the vk that they have given, it has norm square equal to 1. You can just quickly observe it. On the other hand, x vk might not have norm square equal to 1, right? So we have to normalize it. So we have to consider x vk by norm of x vk. And what will this be? This will be the kth largest, or you can say the eigenvector corresponding to the kth largest eigenvalue of the covariance matrix. And therefore, this is exactly our wk, which is the kth principal component. But now how do you determine this entity, which is norm of x vk? To determine this, I will take norm of x vk square, and that is nothing but x vk transpose x vk, right? And then this turns out to be vk transpose x vk. Now this entity here, right, that is same as lambda times vk. Now this follows from this equation here. So now I can say that this is nothing but equal to lambda or lambda k, because vk transpose vk is also equal to 1. So what I have observed is that x vk norm square is lambda k, which means that the norm of x vk is equal to under root of lambda. So this entity turns out to be x vk by under root of lambda k. So essentially what is happening is that this alpha vector is same as vk by under root of lambda k. So they are asking for the value of alpha 2, that is the second component. So the second component of vk by under root of lambda would be, you're looking at the second component of vk, which is 3 by under root 54 divided by the under root of 10. So 3 by under root of 54 times 1 by under root 10. Now this turns out to be approximately 0.13. Alright, so here we have a data set x1, x2 up to x50, and all of them are elements of r to the power 1000. After performing PC on the data set, the residues become 0 at the fifth round. What does this mean? This means that the eigenvectors v1, v2 up to v5 are fully able to capture the patterns in the data set, which means, which also means that these are the eigenvalues or the eigenvectors corresponding to the covariance matrix of this data set. In fact, these are all elements of r to the power 1000, right? What does this mean? This means instead of representing x1, what I can represent is a projection of x1 onto w. Now, what is w? W is nothing but the span of v1 up to v5. Similarly, I can represent all of these xi's as a projection of xi onto w. Now, it turns out that to store these projections are actually easier than storing the original data set. So if you store the original data set, it will take you 50 times 1000, that is 50,000 total numbers that are required to be stored. But if you are projecting, what does it mean? It means each projection can be written as summation of alpha I vi, right? Now there are 5 alpha i's for each xi. So there are 5 alpha i's for each data point xi, and alpha i's are all scalars, right? And how many vi's do you need to store? There are 5 vi's, but each vi takes up 1000 numbers. So 5 vi's will take up 5000 numbers. So alpha i's will be a total of 5 times 250, sorry, 5 times 50, because there are 50 data points. So that turns out to be 250, and VIs take up 5000. So a total of 5250 are required to store this data set instead of original 50,000. Okay, so here we have 3 data points, x1, x2, x3, and we need to run standard PCA. The first question says, what is the covariance matrix? And the second question asks for the variance along the first principal component. So to find the covariance matrix, it is nothing but 1 by n times xc transpose, where xc is the centered matrix. So what is x here? X is nothing but 0 0 1, sorry, 2 1 1 2, and the mean x bar is 1 1. So xc is nothing but minus 1 minus 1 1 0 0 1. Now if I do 1 by 3 times minus 1 minus 1 1 0 0 1 multiplied with its transpose, which is minus 1 minus 1 1 0 0 1, it gives me 1 by 3 times 2 1 1 2. So this is my covariance matrix. Now let us say that V1 is my first principal component. So suppose V1 is my first principal component. What does that mean? That means CV1 is equal to lambda 1 V1, because it has to be an eigenvector of the covariance matrix, and it has to be of size 1. Now this means V1 transpose CV1 is equal to lambda 1 times V1 transpose V1, which is nothing but lambda 1. And what is this term on the left? This term is nothing but the variance along the first principal component. In fact, the variance along any direction is nothing but you do W transpose C times W, right? And it turns out to be the largest eigenvalue of the covariance matrix. So our ultimate aim is now to find out this largest eigenvalue of the covariance matrix. In order to do that, I'll have to solve for the characteristic equation of the covariance matrix. But instead of that, let me just solve for the characteristic equation of 2 1 1 2, and let me ignore 1 by 3 as of now. So I will get 2 minus lambda 1 1 2 minus lambda. This is my characteristic equation, setting the determinant of this to 0. Now solving for this, I'll get 2 minus lambda whole square minus 1 is equal to 0. That is, lambda should be 3 and 1, and the largest eigenvalue is equal to 3. But now I have ignored the 1 by 3 outside, so I'll have to pull it in, and I'll have to say that for the covariance matrix for C, the largest eigenvalue is equal to 3 by 3, which is equal to 1. Right? So the variance of the data set along the first principal component is also equal to 1. So that is the answer to the second question. Alright, so here they're asking for the residues after projecting the data points onto the first principal component. So what are residues actually? It's nothing but xi minus xi hat. Okay, what is xi hat? Xi hat is actually the projection that you obtain by projecting the data point xi onto the first principal component, which is in our case, let me call it v1. Again, while projecting, you have to use the centered data points and not the uncentered data points. So the projection of x1 onto v1 is given by x1 transpose v1 times v1. Now this formula assumes that v1 is a unit vector. So assuming that v1 norm is equal to 1. Now this turns out to be minus 1 times 1 by under root 2 1 by under root 2 whole multiplied with 1 by under root 2 1 by under root 2. Okay, now how did I get 1 by under root 2 to be v1? For that, let me go back to the previous equation and let me put or plug in lambda is equal to 3 in this matrix and solve for 2 minus 3, which is negative 1, 1, 1 and negative 1 times, let's say v11 and v12 equals to 0, because I have to put in the value of lambda and solve for the eigenvector. So that is a standard way of figuring out what is the eigenvalue and eigenvectors. Now solving for this, it gives me that v11 and v12 are the same. That means that 1 1 is an eigenvector, but now I have to normalize it, so I will take 1 by under root 2 and 1 by under root 2. So that is how this is my first principal component. This is my first principal component. So that is why I used 1 by under root 2 1 by under root 2 here, and this turns out to be minus 1 minus 1. So what is this? This is my x1 hat, right? Similarly, I can compute the projection of x2 and it turns out to be half comma half, and the projection of x3 onto v1 turns out to be half comma half. So now to compute the residues, I just have to do x1 minus x1 hat, which is 0 0. x2 minus x2 hat is half minus half. Okay, why is this half minus half? Because we are using x2 as 2 comma 1. We are using the centered data points, not the uncentered data point. Sorry, not 2 comma 1, 1 comma 0. We are not using 2 comma 1. We are using 1 comma 0. And similarly, x3 minus x3 hat turns out to be minus half and half. Now this is nothing but the second option. Alright, so here the question is, let K be a valid kernel such that Kxy is equal to phi x transpose phi y, and phi is a map from Rd to R capital T. And they have given some function K1 which relates with Kxy. And the question is to find phi 1 such that K1xy is nothing but phi 1x transpose phi 1y. Right? This is pretty straightforward. We just have to write this as 100 times Kxy. So instead of Kxy, let me write phi x transpose phi y divided by under root of Kxy, which is again under root of phi x transpose phi x, and under root of Kyy would be under root of phi y transpose phi y. Now this can be written as 10 times phi x whole transpose 10 times phi y, and it is divided by the norm of phi x and the norm of 5i. Now this is not, so this actually means that if I take phi1x to be this entity, then I can write it as phi1x transpose phi1y. If I take phi1t to be equal to 10 times phi t divided by norm of phi t. Now this is nothing but the third option. Alright, so here the question is that the kernel PCA with a polynomial kernel is applied on the following dataset with three features. The kth principal component is given, where phi is the transformation kxij equals 1 plus xi transpose xj whole square. So this is actually a polynomial kernel with degree 2. So the kernel matrix can be written as 1 plus x1 transpose x1 whole square, 1 plus x1 transpose x2 whole square, and this term, the term here will be same as the term here because the kernel matrix has to be symmetric. 1 plus x2 transpose x2 whole square, right? This is my kernel matrix, and this turns out to be 2 square, 1 square, 1 square, and 2 square, which is 4, 1, 1, 4. Now the question is to find the centered kernel matrix Kc. Again, this formula is not very relevant, but you can also use this formula, but it will take more time. Instead, if you use the famous formula Kc equals to k minus 1k minus k1 minus 1k1. So this formula represents how to obtain the centered kernel matrix from just the kernel matrix. And here 1 is nothing but the matrix filled with 1 by n's in general, okay? But in this case there are only two features, so it will be 1 by 2, 1 by 2, 1 by 2, and 1 by 2. Now if you do this computation, you have to do 4114 minus half 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 times again 4114 minus 4114 times half 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 minus half 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 times 4114 again multiplied with half 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 half. Let me write it here. Now if I do this computation, it turns out to be minus 1 minus 4 minus 4 minus 1 plus 5 by 2 5 by 2 5 by 2 5 by 2, and ultimately you'll end up getting 3 by 2 minus 3 by 2 minus 3 by 2 3 by 2, and this is nothing but the second option. Okay, so here we have to compare k-means and k-means plus plus, right? So k-means plus plus is just another variant of k-means, where the only difference is that the initialization is different. For example, in k-means algorithm, the initialization of the centroids happen randomly, but in k-means plus plus it follows some procedure. Let's see what it is. So let's say you have a data set D x1 up to, let's say, x capital N, and each xi is in some RD, and let's say we want to produce k clusters out of these data points. So the initialization algorithm for k-means plus plus, initialization algorithm for k-means plus plus, first of all, pick the first centroid randomly. Pick the first centroid randomly. Let me call it mu1. After this, for every data point xi, you compute the distance between the data point and mu1. So distance between mu and let's say xi. After computing the distance of each data point from mu1, so this is mu1, then you have to compute, then you basically have to normalize it. That is by dividing the distance by the sum over all the di's. So let me call it di upon summation of dj, j running from 1 to capital N. So once you have allotted these probabilities, these so-called probabilities, because all of them will be in the range 0 to 1 and all of them will sum up to 1. So you can think of them as probabilities. And you have got a probability for each data point, right? So the next idea is to choose the next centroid randomly. And how do you choose it? You choose it randomly, first of all, and it's not uniform random. Instead of uniform random, you have x1, x2 up to xn, and you assign it a PMF, p1, p2 up to p capital N, right? So this is the PMF, or you can say that you are choosing x1 with probability p1, x2 with probability p2, and so on. So what does this mean? This means that the data points which are far away from mu, so data points which are far away from mu, they will have a higher chance of being selected as the next centroid. So they have a higher chance. Now after this, you just repeat these steps, repeat 2, 3 and 4 until all centroids are chosen. Until all centroids are chosen. This is the initialization algorithm for k-means plus plus. One more thing to notice is that if there are several mu's chosen, let's say you have chosen mu1, mu2 and mu3, and then for mu4 what you do is that you compute di to be the minimum distance between, let's say, mu j and xi. Okay. And minimum is running over j. Okay. So basically di measures the distance of the data point xi from its very closest centroid. Whatever is the closest centroid, from that what is the distance, right? So data points which are very far away from all the centroids, they will have a higher chance of being selected as the next centroid. So this is the initialization algorithm for k-means plus plus, and the question basically asks us how this happens. Okay. So the answer is the second option. It improves centroid initialization by spreading them out, leading to better separated clusters. This is correct. It ensures the algorithm converges in a fixed number of iterations. This is not correct. It automatically calculates the best value of k. This is also not correct because k is a hyperparameter and it is typically chosen using hyperparameter tuning, using a special method called elbow method. The last option says it removes the need to run the algorithm multiple times. This is also ridiculous. Alright, so here we have that in a k-means algorithm with k equal to 3, the objective value function is recorded after each iteration as follows, and the objective value functions are given. Observe that the objective value functions are always decreasing. So in fact, this is a very important property of the objective value function f in k-means. The most important property is that it keeps on decreasing. So it is monotonically decreasing. Monotonically decreasing. In fact, it decreases strictly. And This happens until convergence. What do I mean by convergence? By convergence, I mean that the clusters are not getting updated anymore. Convergence means that clusters are not updated anymore. And here you can see that from 800 to 500 they have changed. From 500 to 400 they have changed again, but after this it is not changing anymore. What that means? That means that the convergence has already happened, and that is exactly what the question asks for. At which iteration is the algorithm most likely to reach convergence? And the answer is iteration 3, because after this point the objective function value has not reduced anymore. So this is the correct option. One more thing to note is that in k-means algorithm, it is not necessary that the convergence is happening to the optimal point. It could be to a non-optimal point as well. So let me just make a note of it. This point where it has converged, or you can say the algorithm has stopped, this need not be at an optimal point. Alright, so here we have a random sample x1, x2 up to xn, which is taken from a Pareto distribution, and the density function or the probability density function of the Pareto distribution is also given. The 5 sample observation are also given, and they are asking us to find the maximum likelihood estimator. So in order to find the maximum likelihood estimator, first we have to find the likelihood itself. So the likelihood is nothing but the product of the PDFs, which turns out to be theta to the power 5 product I running from 1 to 5 xi to the power minus theta minus 1. Now typically we want to maximize this likelihood by maximizing its log function. So we maximize log L, and why we do it? We do it because log is a concave function and it's also monotonically increasing. So it will turn out to be 5 log theta plus minus theta minus 1 times summation log of xi. Now to solve it, I'll have to take derivative of this with respect to theta, and it turns out to be 5 by theta plus negative of summation log xi. And to find out that particular value of theta for which log L is maximized, we'll have to set it to 0 and solve for theta, and that gives us theta hat MLE, let me call it MLE for maximum likelihood estimator. That turns out to be 5 by summation log xi. And here notice that log is the natural log, or typically people write it as ln instead of log. One more thing that you have to check is that you need to take the double derivative, and you can see that the double derivative is minus 5 by theta square, and this particular value is always negative, and this ensures that theta hat MLE actually maximizes this function and not minimizes it. So now you have to compute 5 by summation log xi for all these data points, and it turns out to be approximately 1.148. Alright, so here we have a question on the EM algorithm. So the EM algorithm setup is like this. You have some model parameters theta. You have the data which is observable, which we call as x. So x is the observable data, and z is the hidden data, or you can say the latent data, latent variable. And the EM algorithm goes like this. You start with a random initialization of the parameters called theta naught. Then you estimate the latent variables. In fact, you estimate probability theta t z given x, right? And then in the next step, you compute the next iteration of theta, which is theta t plus 1, by maximizing the q function. So this is the q function here, and the q function is the expectation of log p theta t x comma z. Now this p theta t z given x is used to compute this, and once we have the numerical value of this, or this as a function of theta, and then we can maximize with respect to theta and obtain the next iteration. Typically this step is called the E step, and the next step is called the M step. So as per the EM algorithm, the first option says E step estimates the latent variables in the data set, and M step maximizes likelihood over the model parameters. This is actually correct. In fact, this turns out to be some variant of the likelihood of the model parameters. The second step says estimates the number of latent variables in the dataset. This is not correct. Third option is also not correct. The fourth option is also not correct. So only the first option is correct in this question. Also, if you want a detailed explanation of EM algorithm, you can let me know in the comments down below. Alright, so here we have a question on both EM algorithm as well as the Lloyd's algorithm. So what does it say? The first option says EM algorithm converges to a global optimum. This is not true, because most of the time the likelihood that we want to optimize is some multimodal likelihood. It might look something like this. And depending on where we start, let's say if I start from here, it will carry it forward. The EM algorithm will pull it forward in the sense it will pull it upward into the nearest local minima, and it will stop here. Stop at this not local minima, local maxima. So the EM algorithm converges to a local maxima. So this option is not correct, and that local maxima need not be the global maxima all the time. The second option says Lloyd's algorithm converges to a local optima. This is correct, because at every iteration in the Lloyd's algorithm, you can observe that f of z t plus 1 is strictly less than f of z t. So it will converge to a local minima. It will land in a local optima. Will land in a local optima. The third option says poor initialization does not affect the clusters produced by EM algorithm. This is wrong, because it does affect. In fact, initialization affects both EM algorithm as well as Lloyd's algorithm. That is one of the reasons why we have smarter methods for initialization like k-means plus plus. The fourth option also says that poor initialization leads to slower convergence of Lloyd's algorithm. This is correct actually. Oh, the third option is actually wrong, because it does affect the clusters. Poor initialization leads to a slower convergence. In fact, this is why we need k-means plus plus. Then the last option says Lloyd's algorithm is sensitive to the number of clusters. This is also true. In fact, if you have if your data actually has 3 clusters and you run the k-means algorithm using 2 clusters, then it will give you very ridiculous results. Alright, so here we have a question on gradient descent and stochastic gradient descent. So what gradient descent does is that it updates the parameters of a model by this particular rule. Theta t plus 1 is equal to theta t minus eta times gradient of the loss function. So L here is the loss function, and in gradient descent, this loss is taken over the entire data set. This loss is taken over the entire data set. Remember that the loss function in linear regression looks like this, something like I running from 1 to n, W transpose xi minus yi whole square. And if you're including all data points, then it is gradient descent. On the other hand, in stochastic gradient descent, you do not include all the data points. So it will look something like, let's say, theta t plus 1 is updated as theta t minus eta times grad of some li, where the loss here is taken for one randomly sampled data point. So loss is taken for one randomly sampled data point. There are other variants to this, things like mini batch gradient descent and all, where instead of one data point, you take multiple data points, right? Again, not the entire data set, because computing the loss function over the entire data set and taking the gradient, especially taking the gradient of it, is computationally very, very expensive. Okay, so what is the primary difference between gradient descent and stochastic gradient descent? One difference is that gradient descent is typically slower, whereas stochastic gradient descent is faster, but you don't get things for free. So in gradient descent, there is a theoretical convergence guarantee, which is you are sure that it will converge. On the other hand, with stochastic gradient descent, there is no theoretical guarantee. On the other hand, it is also important to note that in stochastic gradient descent, in practice, it works very well. In practice, it has been found that it almost converges most of the time. Okay, so the question actually asks us about linear regression. So before saying, I want to point one more thing, that in gradient descent also, the theoretical convergence guarantee is only to a local optimum. To a local optimum. It is not to global optimum. But in case of linear regression, our loss function looks like this. Summation W transpose xi minus yi whole square. And this is a function of W, right? Because we are optimizing over W, the weights. And it is a convex function. Because it is a convex function, the local optima and the global optima will be the same. And because of that, we can say that the gradient descent will converge to a global minima. And this is because for linear regression, for LR, the cost function or the loss function is convex. If it had been non-convex, then this guarantee would not have been possible. The second option is definitely false. Stochastic gradient descent is guaranteed to converge. This is false. Gradient descent will take lesser number of iterations to converge to a local minimum than stochastic gradient descent. Okay, so one more difference between gradient descent and stochastic gradient descent is that each iteration in gradient descent takes too long. Each iteration takes too long. Takes too long. On the other hand, in case of SGD, one iteration is very fast, but it takes more iterations to get to a good approximations. To get a good approximation. So the trade-off is between, because see, in stochastic gradient descent, we are only taking the gradient of the loss over one data point. So definitely one iteration will be very fast. But again, it need to capture a lot more data in order to be good enough. That is why it takes more iterations. So the last option is also correct, because gradient descent takes lesser number of iterations, although overall it may be slower. Alright, so this is a very classic question on linear regression. But the only difference is that they have mentioned the model to be y equal to wx. So the model actually is y equals w1x, or you can say w1 xi1. Okay, so let me name it wi. w1 xi1 plus w2 xi2. Remember that this is not square, this is just an index 2, plus epsilon, because I am just naming these guys x1 and x2. Okay, now what will be the loss function? The loss function will be summation of yi minus w1 xi1 minus w2 xi2 whole square, right? I running from 1 to 4 because there are 4 data points. Now if I take derivative of this with respect to w1, remember that in least squares we take derivative and try to optimize, right? In fact, we take derivative and set it to 0 and try to find out what is the value of w1 and w2. So this will turn out to be minus 2 summation yi minus w1 xi1 minus w2 xi2 times xi1 equal to 0, because we have to set it to 0. Similarly, I can do it for w2 as well. It will be the same thing, the same term, with only one difference, which is that outside we will have xi2. Okay, you can just verify this differentiation. This is very straightforward. Now if I rewrite this, let me rewrite this in a better manner. It turns out to be summation xi1 yi minus w1 times summation xi1 whole square minus w2 times summation xi1 xi2 equal to 0. This is my first equation. In fact, these are called normal equations, by the way. These are called normal equations. And what is my second equation? My second equation would be summation xi2 yi minus w1 times summation xi1 xi2 minus w2 times summation xi2 whole square equal to 0. Now these terms, xi1 y1, xi2 y1, and all of these terms can be computed using this data set, right? And if I compute all of them, then this term turns out to be minus 30. This turns out to be minus 140. This term is again 30. This term is 85. This term is also 30. And this term is also 30. So now we have two equations and two unknowns. What are the two unknowns? W1 and W2 are the two unknowns. And now this can be solved using simultaneous linear equations. So I can write 30A or 30W1 plus 30W2 equals minus 30, and 30W1 plus 85W2 equals minus 140. Now if I subtract the second one from the first one, I'll get 55W2 equals minus 110. This turns out W2 equal to minus 2 and W1 will be equal to 1. And this corresponds to the second option. So second option is the correct answer. Now the next question says to find the mean squared error for the training data set. Now if you use this W1 and W2 and try to predict y hat, what will you get? You'll get the first term would be 4 minus 2, the second one would be 2 minus 16, the third one would be 1 minus 8, fourth one would be 3 minus 4. This would be 2 minus 14 minus 7 and minus 1. You can see that the predictions are exactly the same as the observed values. So the mean squared error for the training data set is equal to 0.